In this last video, we are going to give you an introduction into dielectrophoresis. And as a motivation, you can have a closer look on at the video on the right-hand side. So the black parts are electrodes, and the little particles that you see within the liquid, those are cells. If you now apply voltage to the electrode, you can see that the cells apparently align alongside your field lines. And this effect can be used in microfluidics as well. And as you can see, this effect is not very strong, because if you're further away from the electrodes in these areas, you don't see the influence of the electrodes anymore. What's the difference to the considerations that we did so far? On the right-hand side, you can see the classical description that we used within the first three videos. So a positive, negative electrode, and you have parallel field lines in between. If we now shrink the negative electrode on the right-hand side, you will see that the distance between our lines is bigger at the positive electrode than it is on the negative electrode. This means that there's a gradient in our electric field. The second thing that you have to consider is that the sphere that is in between the electrodes has another permittivity than our liquid around the sphere. Why is this important? If the permittivity of the liquid is bigger, you can consider in a simplified model that there's a larger number of positively charged or negatively charged ions at the respective side of the electrodes, and larger in the sense of there are more ions outside than inside of the sphere. So the inside charge will be cancelled by the charge of the liquid. So basically this positive sign cancels the negative sign, and there will be one positive sign left. And on the right-hand side, there will be one negative sign left. And this means that there's a repellent force in direction in between those negatively charged areas, and there's a repellent force between the positively charged areas here. And as the gradient, so the distance between the lines, is bigger on the left side of the sphere than on the right side, the forces, the repellent forces of the right side will be stronger than the repellent forces on the left side. And this is why we get the dielectrophoretic force in direction, in the left direction in this case. You can turn it also around. So if you now consider that the permittivity of the liquid is smaller than the permittivity of the sphere, we have the other situation. So there are more charges close to the boundary within the sphere. And then you have to consider the attractive forces from the electrode to the sphere on both sides. And obviously, as the lines are closer on the right side, the attraction force on the right side will be stronger. And then the particle will be moved in the right direction in this case. The just presented model only helps to understand why there is a force at all in these situations, but to really calculate the force is way more complex. And here on this slide, you can see an example how the force looks like and what parameters are important. So in this case, the equation describes the force on a spherical particle between a flat and a spherical electrode with the radius A, and the sphere has the radius R. And what you can see is that the force depends obviously on the permittivity of the liquid and the sphere, but it also depends on the radius of the particle, as well as the gradient of the electric field, which again depends on the size of your spherical electrode. If you go now a step further and use alternating current instead of direct current, you can make sure that the monopoles do not change their position due to electrophoresis, because they move in one direction, for example to the right, and then move in the next step back to the left to the same amount. And you can make sure that dielectric double layers are of no importance. But nevertheless, you can use the alternating current as driving force based on dielectric principles. All right, that's it for the electrokinetics module. And let's shortly summarize what you've learned during the 4 videos. So first, you should be able to name the different principles of electrokinetic transport. So there is electrophoresis, there's electroosmosis, and finally there is dielectrophoresis. You should be able now to describe the basic models for electrical double layers, and the main keywords that you should remember are the different models and what differs the models. So there's the Helmholtz, the Guy-Chapman, and the Stern layer model. And basically they all consider similar effects, but the weight they give to these effects are different. And here is always important to remember that the models consider either a rigid layer, or they also include additionally diffusion effects within the liquid. And finally, you should be able by now to describe electroosmotic flow. And here is, for me, the key point is to understand how this electroosmotic flow builds up. So you have to remember that there's an electrical double layer close to the wall, and this leads to a locally negatively or positively charged area, which is then attracted by the applied voltage. And by dragging all the different and all the other fluid layers with it, this outer layer is the driving force that builds up your electroosmotic flow. Thank you for paying attention and watching the videos, and please don't hesitate to ask us questions if you want to know more about this topic.